I'd like to welcome all of you to this colloquium by Laura Waller as part of our distinguished lecture series. So Laura is visiting Germany on a Max Planck-Humboldt medal prize, but she's a professor in electrical engineering and computer science at UC Berkeley, and is quite well known actually for what the title says in the field. So Laura did her undergraduate and graduate work at MIT. I think it would be fair to say that she was trained as an engineer, but I think we all know many people from engineering who cross over and work on areas especially related to microscopy. So the borders between physics and electrical engineering then become very, very fluent. She, after her PhD, she did a postdoc at Princeton, and then I believe you got the position at Berkeley, and she's been there since. And there are lots of interesting works that I think we will hear about, different flavors. I don't know exactly what you have as part of your presentation, but there are lots of contact points with various groups here and at MPZ-PM. So I encourage you to take the opportunity to interact afterwards. If you want her to see your labs or experiments, feel free to get in touch. You'll be around for all of next week as well.
Yes.
So, yeah, great. So with that, I suggest we pass on the floor to you.
Thank you. Yeah, I'm here to visit and learn about what you guys are doing and think of like ideas and discussions. So please feel free to contact me to set up a time or just show up next week. I'm on the 3rd floor. Colin and I are sharing an office. That's the point of visiting, so don't be shy. Okay, so I want to talk about our work in computational microscopy. This is like a general design philosophy for designing imaging systems whereby you think about the hardware and the software together. And you try to holistically design in terms of what you can do with optics and what you can do with computation. And so that often means that the pictures that you're capturing look nothing like the final image that you're going after, but they contain the information that you would like to get at, and then you probably need to solve some sort of inverse problem to reconstruct the image afterwards. And there's various different implementations of this. But my lab specifically does both hardware and software. And I think having expertise in both of these areas is a really great way to find synergies that you otherwise wouldn't if you tried to like just get an optical designer to do the best they could and then hired some AI to then like extract the information from whatever captured images you had taken. So I want to like start with a really old project. I'm going to start really old and go to the newer stuff because it all builds on each other. This is like one of the first projects in my group. And it was like we originally built this to copy Cheng-Huiyang's lab. It was this LED array microscope. So this is the oldest infinity corrected microscope I could buy for the very cheap at the time. And all we did was remove the illumination unit and put in this LED array. Adafruit is literally a toy company. You can buy these things dirt cheap online, and it's all the LED array is controlled by some Arduino microcontroller so that you can pattern the illumination. So this thing's just sitting above the sample. And it's big. It's like 5 by 5 inches, and it's sitting a few inches above the sample. So when you light up different LEDs, you're basically illuminating the sample from different angles. So the sample's small, and this thing is big. So essentially, the light from each LED is a plane wave at the sample coming in from a different angle. And you can treat it as spatially coherent plane wave at the sample place. So we're like doing this like disco party pattern, and I'll explain later where that comes from. But then we can do all kinds of things with this. This is a really cool example of a computational illumination platform where this same like simple, cheap hardware, it's very practical to make, can do all kinds of different things depending on how you pattern the LEDs and take the images. So like You can do different like contrast modes for label-free contrast. So if you just light up any of the LEDs in the center, you get a bright field image. If you light up the LEDs that come in at angles that are beyond the acceptance angle of your microscope, so your numerical aperture defines an angle of acceptance. If you turn on all the LEDs outside of that bright field circle, you get a dark field image. And if you turn on any asymmetric illumination patterns, you're going to get some phase contrast. So this looks like DIC. It's not quite DIC. But then you can just time interleave these. You don't need to like swap in and out objectives to change your contrast mode, and you can sort of do all these three at once. So the phase contrast one I love talking about, and Colin's here. This was like something that Colin's lab was doing when I was visiting them in Singapore. I was in the Singapore MIT program in grad school, and I spent some time at their lab when I was in Singapore. And I remember like Shalin, who's this guy, was playing around with putting in like piece of cardboard into the illumination, into like the condenser, to try to like make this asymmetric illumination. So if you do like a half circle, you get some phase contrast. Half circle on bottom, you get some phase contrast. If you add them together, you get bright field, and if you subtract them, you get this like DPC contrast image, which disappears all of the amplitude information because it's fully asymmetric. And so you can then get quantitative phase from this. And so this was their thing, defining these like half circle illuminations. And the LED array is just a really great way to get it because it has like a big area and it sprays out to high angles. So like SLMs can't do that. They don't have a good étendue or space bandwidth product. And the LED array is just really practical for this. So then we can take 3 images and reconstruct phase. So like we initially started with like the 3 half circles, but you can design designer patterns. I think that's what this is, to make it be like more efficient energy information wise. And then you can do fast quantitative phase imaging because you only need a couple of images, and the LED array is always faster than your camera. Okay, so this was cool because I'd been working on phase imaging for a long time from through focus, and through focus just like takes time. You have to move the sample. It's not super practical. This also has some better information properties.
Sorry, what were the things that you put the link on the right?
Make it play. Let me just start it again. This is like vesicle tracking. Something's up with this. The videos have been like compressed or something. You can see it a lot more clearly in the original video. These are some vesicles running around inside the cell.
You know that they're vesicles.
That's what the biologist who gave us this sample told us. So I know as much as I trust that person. All right. Yeah, so the reason why we built this LED array microscope was for this gigapixel imaging or Fourier ptychography. Probably lots of people have heard of it. So this gets at the space bandwidth product like concept. So space bandwidth product is the number of things you can resolve within your image. So it's like if you have good resolution, then you can have little teeny tiny resolvable points in your image. And if you have a big field of view, then you can fit a lot of those teeny tiny points into your image. So you have a large space bandwidth product. And normally in any microscope, like a camera, you have to trade off. You either zoom in for good resolution or you zoom out for big field of view but bad resolution. So with Fourier ptychography, you zoom out, you use a low NA objective such that you get a big field of view, but you can't resolve the smallest features. So you're using your microscope to do the big field of view and you don't have good resolution, but then we do this disco party illumination patterns that I showed you, and you get a bunch of images. Some are dark field, some are bright field, all are low resolution, but they all have different contrast happening, right? So changing the illumination is changing something. Actually, you can see it's lighting up edge effects. And those edge effects, like the dark field images, represent information that's like beyond the diffraction limit of the microscope objective that you're using. But it's not super resolved. But computationally, you can put this all back together and get 7 times higher resolution in each dimension for this case. And in fact, your final resolution just goes as the resolution limit. So it's lambda over 2NA. But the 2NA really comes from going in with one NA and coming out with the other NA. And you assume that they're the same because you're in reflection mode, you'd be having the same numerical aperture. Or you assume that your illumination can only be as large as the numerical aperture of your detection. But now we get to add the numerical aperture of the objective, which is small. It's like 0.1 in this case, and the numerical aperture of the illumination, which is humongous. We can actually, you'll see later we're making domes, we can do 1 for our illumination NA. So then you can get at this like big field of view, but high resolution. And this is all quantitative phase imaging by necessity. But I just wanted to show like the space bandwidth product is really valuable. Like if you were to, the resolution that we get in the end is the same resolution as an 80x objective, which would have this field of view. But now we get that resolution across this much larger field of view. And really like what you're getting here is not so much, you can talk about it as super resolution because it's super resolution from a low NA objective. But I think really what you're buying here is field of view in a lot of cases. These are HeLa cells. This one's like gonna break up and divide into a few cells. And you can see when it curls up in a ball, it would normally like go, if it was in an 80x objective, when it curls up in a ball, it would definitely go out of the depth of field of the microscope and be all blurry. But here we get to keep the original depth of field of the low NA microscope. So there's some nice advantages if you're trying to have like a large depth of field here. You can segment this quantitative phase data. This is my test for is it good quantitative phase data. Quantitative phase is almost always hard to get low spatial frequencies measured correctly. And if you have them measured correctly, you can do segmentation accurately. If you don't, you can't. Yeah?
Would you take a moment to define what you mean by quantitative phase?
So quantitative phase means that I've solved an inverse problem for what is like the phase delay relative, like across the field of view. So it's the relative phase delay in 2D across this field of view that you can like back out from the measurements that you made.
I see. So you're not really talking about the phase of individual like constituents of the cell or something?
Yeah, it's all referenced to some arbitrary reference, 0 phase. So like we can't capture like the piston phase. So we know nothing about like the absolute phase. It's all like relative to all the other points within the field of view. That's pretty standard, I think, for, yeah. Yeah?
Have you ever done like a check where you used a liquid with a non-refractive index to see if you get the right phase?
So you can't just do phase on like just a flat liquid, but we can check, like, so we have this benchmark technology sells a phase resolution target. It's like the Air Force resolution target, but they have the star shape, and they have them at different heights, and you can check that you've gotten the height correct because they tell you the refractive index. And so if it's in air and you know the refractive index, you know what the phase shift should be for a given height, and you can check it that way. So they have like a range of different heights. Yeah. So this is all old, so I don't have those slides handy, but yes, we've done that, and it's like pretty good. The thing about quantitative phase is that you're solving a nonlinear optimization problem. And so like I can prove to you that I can get it really accurate on that test target, but it doesn't really mean that like I'm going to do exactly the same accuracy on cells. Cells are actually easier to image, and so they might actually be doing better because they don't have sharp edges the way that like the test target does. So there's a lot of like, yeah, you can show how well you're doing in one case, but it doesn't mean that it's going to apply always for other cases. Yeah?
I was wondering how complicated the numerics in the problem are. Is it like just subtracting images?
It's a nonlinear optimization. I'm going to talk about it in a second. So the DPC is just a deconvolution, essentially. So the original derivation was analytical for the half-circle illumination, but our illumination is not exactly a half-circle. It's like a bunch of dots within a half circle, and we also do it with like arbitrarily different patterns. And so you model the illumination pattern and then do essentially a deconvolution. Any other questions here? Okay, so let me talk about how this Fourier ptychography goes. So the idea, it comes from Fourier space. Fourier ptychography. Ptychography already existed. Fourier ptychography is the version of it in Fourier space, but I argue that it's very practical for biological microscopy. So you start with this low NA objective, and if you think about the sample's Fourier space, so this is like spatial frequency in X, spatial frequency in Y of the sample. And so a low NA microscope will only measure a small bandwidth of spatial frequencies. You can think of it as angles as the same thing as spatial frequencies. They're just related simply. And so, so you have a small range of angles, small range of spatial frequencies, small bandwidth, poor resolution. So then when I illuminate from off-axis over here, that's a phase ramp in real space. So in Fourier space, that's a shift. So that green circle shifts. So now I collect an image that is the intensity image in real space from a set of spatial frequencies that comes from over here. So it's outside the passband of the objective, which means it's a dark field image, and it's lighting up all these vertical edges because it's over here. If I light up this one up over here, it's gonna light up all the horizontal edges. And these are like sub-resolution features that light up because that's what dark field is doing, right? It's illuminating from high angles, sample scatters, and then I'm only collecting the stuff that's scattered off from a high angle. And so this is the set of spatial frequencies I get from illuminating over here. That doesn't mean that I can like get super resolution from it yet. So if I go and turn on one LED at a time, spinning through the array, and collect a whole bunch of images, each from a different part of the sample's Fourier space, then I can of course fill in this larger aperture, and this is called synthetic aperture imaging. So filling in this larger aperture means I have a larger overall bandwidth of the collected images, and so I should be able to get a higher resolution, but not so fast. I've only measured intensity, right? So I only measured absolute value squared of, like, these circles are representing the frequencies, but I only measured absolute value squared. In Fourier space, that's an autocorrelation, so there's some ambiguity between the thing and its conjugate. But this is what Fourier ptychography is all about, or ptychography is all about. I can put this into a big optimization inverse problem and solve for the Fourier space across the whole larger aperture. So it's like a big optimization problem that is stitching together all of these like parts of Fourier space, but also doing a phase retrieval. So you can see like all these circles are overlapping severely. That is not by accident. That has to happen or the phase retrieval won't work. And if you do a sufficient overlap, this optimization problem will generally converge. So we're like solving for the whole thing, doing a phase retrieval plus synthetic aperture. I'm going to talk about it later, but we also solve for the pupil function, which is the wavefront aberrations in the microscope, and we basically digitally remove them to make the images look nicer. So how you solve that optimization matters. The standard way and the original way for Fourier ptychography was like this like Kirchberg-Saxton, sometimes called ping pong algorithm. It's basically just first order gradient descent with a specific step size. And it works great if you have a lot of overlap. If you try to reduce the overlap to the bare minimum, then it starts to bring in artifacts. But it's super fast. You can type it out in a few lines of code, and it's really easy to understand. If you do like second order optimization, so like not just looking at the first derivative of the cost function, but also the second derivative, which is a Hessian, then you can get much better result from the same data set. It's just really slow. And so here's some commentary on speed versus accuracy. So we wanted to like get the accuracy of this one with this and the speed of this one. And you have to trade these off to some degree. What we came out with is this quasi second order method. So computing the Hessian is really expensive computationally because it's a matrix. It's not just a single gradient. So what we do is we just compute the diagonals of the Hessian. That's good enough to get your like updates to be better. And then we can get like a good result fast enough. So this is just a patch. So you have to multiply these times by like however many patches you have in your image. If you're trying to do a gigapixel at like video times, then these times can explode really quickly. Okay, what's next? Okay, so this overlap is necessary, but it's annoying because it makes I have this like thing about, I always ask people about like the data efficiency rate. It's like, how much data did you collect? How much data are you reconstructing? And so like compressed sensing says you can sometimes solve for more data than you collected. That's really cool. But in this case, we're collecting almost 10 times more data than we are reconstructing, which seems bad. But you can't just make these circles further apart. The phase retrieval just won't work. It will fail. Yeah?
How do you quantify information?
How many pixels did I collect? How many pixels do I reconstruct from that? So if I collect 100 images at 1 megapixel, that's 100 megapixels. am I reconstructing less or more than 100 megapixels? And I would like the number to be 1-to-1 because I'm not doing compressed sensing and I don't want extra data. Okay, so we couldn't just open up these circles. So what Lei came out with was this disco party pattern, which is basically just, it does DPC, so it does the half circles you can see in the middle there, the half circles, and then like random 8 LEDs chosen, and then you choose another 8 LEDs till you fill them all in. And you can actually fill in this larger circle about 8 times faster, but also you have 8 LEDs on at a time, so it's 8 times brighter. So this goes almost 100 times faster when you do this, after we like fix some hardware as well. And then Michael took it even further and did some like fancy machine learning end-to-end optimization that I don't want to talk about, but this was a series of 3 papers. It was like very highly computational stuff to try to learn the best LED array patterns. So we told it you're only allowed to use 8 LED array patterns to get whatever bandwidth we were going after image. And these are the ones that it came up with. A little bit surprising, not random at all. It's like these little slices of pie here. We have some explanations to that. It does something like DPC for the 2 bright field images, but we end up being able to get as good a result with 10 images as we used to need 90 images for if we were doing 1 LED at a time. Okay, I'm not going to get into that too much, but I need to say that we gave up on the Adafruit LED array really quickly. So I said it's a toy. It's really cool that you can buy this $20 toy and make a super resolution microscope out of it. But it's a really terrible LED array. You can only really turn on 1 LED at a time, and it just time multiplexes all the rest. So if you want to do anything fast, it's not useful. So Zach, when he came to my lab, had worked on the Duke gigapixel camera with David Brady, and he basically built like the illumination version of it, 3D printed this thing and hand wired each LED and designed all the controllers for it in the first 3 months in my lab, which was pretty awesome. But then came to this design. It's 5 circuit boards with LED arrays, and we outsourced the manufacturing of this, and then you just click the circuit boards together into this quasi-dome thing. This thing has 0.98 NA illumination. You can do arbitrary patterns. It's RGB, and it's very fast and bright. And we spun out what we call a startup company, Spectral Coated Illumination, which in theory is a profitable startup. In practice, it's a box in somebody's garage where if you order one, then we will pull it out of the box and ship it to you. And when we run out, we order 20 more because they're cheaper to order they're cheaper to order in bulk. But these things, like we have adapters, you can just click it into the condenser unit of a standard bright field microscope and get this thing up and running pretty quickly. Okay, so the last piece of this that I want to talk about is 3D imaging. And of course, when you illuminate from different angles, it's a lot like tomography, right? And so it's getting you 3D information. So everything I said so far was predicated on an assumption that the sample was thin and flat in the focus plane. So this like illuminating from different angles only amounts to shifting in Fourier space for like a thin sample within the focus plane. And so now if your sample is thick, this is like 2 resolution targets at different, one's above focus, one's below. And as I illuminate from different angles, it looks like they're shifting. They're like walking across the screen. This is a light field effect, right? Like light fields describes how fast this thing walks across the screen, tells you how far away it is from focus, and which direction it's walking tells you if it's above or below focus. So there's 3D information to be had here. And so we need to update or have like 3D models to account for this if we want to be able to solve with it. So I'm not gonna get into too much about like how we're doing it, but you can get these 3D phase images, which is basically a 3D refractive index map. So phase is a projected quantity. And so once you go to 3D, you're really separating out the like refractive index and the distance part of your optical path length. And so you get 3D refractive index maps. This is one of the first images we did. This is 3D DPC, basically DPC at lots of different planes. And this is mouse embryos to give you a sense of what we're looking at. But what we want to do is to use like the Fourier ptychography data set. So we're just illuminating from different angles through the sample and use only that intensity measurements taken from different angle illuminations to reconstruct the 3D refractive index. So when you set all of that up, there's a lot of prior work on this, mostly theory. And it ends up looking a lot like a neural network where you're trying to learn the weights of the neural network. And the weights are the amplitude and phase delay at each voxel within the 3D object by taking a bunch of measurements, and we know how light propagates between these nodes of the network, which is just diffraction. So we can model that. So like neural networks, it's nonlinear and non-convex, which means we don't know when the optimization is going to work. We don't have good ideas of like how well it will work. We can sort of just try things. It's very black boxish. The good thing is this model fully accounts for how light can bounce back around. As it's going through the sample, it might bounce around multiple times between different parts of the sample. And so it is accounting for multiple scattering. And so we have a chance for the inverse problem to solve the 3D refractive index map with account for multiple scattering through the sample, which was really exciting to me. So if you're solving for the 3D refractive index map, it's actually called the scattering potential. It deterministically describes every scattering event in the volume. That is to say that if you have like light coming into a 3D refractive index volume and you know the refractive index everywhere, you can exactly predict the output complex field from the input complex field. And like this, the refractive index variations are what causes the light to scatter. And so this isn't like statistical scattering, it's deterministic scattering that probably is only going to work for like a reasonable range of scattering. So the idea is if you can measure the 3D refractive index, you can essentially computationally undo all the scattering and get diffraction limited images anywhere within the volume without having sample-induced scattering destroy your quality of image. Okay, so like people have been thinking about this for a while. Optical diffraction tomography has been around for a long time, and most of it until maybe not that, until the last 10 years, has used the Born approximation. So you take the physics and you simplify the physics by making an assumption of weak scattering, which is kind of like an assumption of single scattering, and it makes the math easy. So it means that you can write like a transfer function for input-output complex fields, and that makes everything easy mathematically, but it's not a good model. It doesn't model multiple scattering. So this is like go back to the drawing board, and multiple scattering has always been really hard. There's no analytical solutions to deal with multiple scattering. It's always been thought of as an intractable problem because it is mathematically, but like this is exactly what machine learning is good at, solving impossible problems where like you should be able to get the solution, but there's no obvious way how. So the model we largely use started out in electron microscopy, and it's this idea that you take your sample and you model your 3D sample as a series of 2D layers with light propagating from one side to the other. So primarily, we're just accounting for forward scattering here. And so now each 2D layer of the sample has a given phase delay and a given amplitude, like attenuation. And so you take all of the like 3D information and you lump it into these 2D planes. However, and you should just space the 2D planes by less than the depth of field of the microscope, and this becomes fairly accurate. And then you can easily do these like Fresnel propagation, multiply by the complex refractive index here, Fresnel propagation, multiply by complex refractive index, etc. And then you can easily model how light goes through the sample. And more importantly, it's quick. Fresnel propagation is just a Fourier a convolution, so it's just a multiplication in Fourier space. If you stay in Fourier space, you can also do the complex transmission functions in Fourier space. And so then you can do all of this quick, which is super important because we need to put this into a big optimization loop that's like, guess the 3D refractive index, figure out what all of the measurements should have been, figure out how they're not the same as the ones I measured, and then update the 3D refractive index and do the whole forward process again. So like we can't take minutes per iteration. We need like less than seconds. Okay, so Michael Chen in my group came up with like a slightly more accurate version of this where he says instead of 2D slices with free space propagation between, he's gonna chop up the 3D sample into a bunch of slabs. Each slab now can have the Born approximation be valid in it, but multiple scattering will be captured by breaking it up into many slabs, and then between each slab you can have multiple scattering. And so the benefit of this is it's more accurate at high numerical aperture, and it gives you backscattered light, so you could include all of the stuff that goes back and forth and eventually comes out the other side. Biological samples tend to be mostly forward scattering, so you largely don't really need that, but maybe in some cases you do. Okay, so here's a sample. This is just a cell. And now I'm doing my illumination from different angles spiraling outward. We switched here to an LED, to a laser illumination with a galvo because we can have more fine control of the angles. And as you see, as I illuminate from higher and higher angles, you see that. So remember we said we come in at an angle and it shifts things in Fourier space. So I just took the Fourier space of this video. And so it shifts things in Fourier space, and you see the circle shifting, and you see the conjugate circle. Because in Fourier space, intensity is an autocorrelation. So you see the circle and its conjugate in Fourier space. And if the sample is single scattering or weakly scattering, all of the energy, scattering energy, will stay within these two circles. And this becomes really easy. You can then circle find and fit to the angles nicely, etc. But this is a weakly scattering sample. And so everything fits within these two circles. And then when I solve the 3D refractive index, it doesn't matter if I use the single scattering or multiple scattering model. They both look essentially the same because single scattering was accurate for this particular sample. So this is a slice of the 3D refractive index from the full 3D reconstruction. But what I want to show is different samples with more and more scattering. And what you see is, here's a C. elegans embryo, and you can already see the raw data here looks kind of speckly. And now the two circles are there, but there's stuff happening outside the two circles, and it can only get there by multiple scattering. So this has some multiple scattering, and now you see a difference. There's something compressed about these images. There's something weird going on. But now you can see a big difference in the reconstructed refractive index. This one keeps the low spatial frequencies a lot better than this one, because the single scattering approximation is not really that valid anymore. Okay, and then this one's really highly scattering. The two circles are almost completely gone, and now you see a much bigger discrepancy between these two, and the refractive index values here should be more accurate. So we have some phantom benchmarks where we know their refractive index, and we can check with those, but we don't know exactly what we should be getting for C. elegans, so again, how quantitative it is up to you on that case. So here's putting this all together. This is a 15 gigavoxel reconstruction of a C. elegans worm. And you're just seeing the central slice of the 3D reconstruction and the refractive index differences across it. So there's a lot of high contrast refractive index areas that will scatter the light. And so if you just tried to focus the microscope in the middle plane of this C. elegans, it will look really blurry because of sample-induced scattering, but now it's been digitally removed by solving for the whole 3D refractive index here. Okay, so lest you think that this is a great idea for all kinds of different scattering things, I have to caveat this with we run out of compute eventually. Those are all static samples, so we took data for minutes, and we ran reconstructions for that 15 gigavoxel thing was a day's worth of reconstruction time. So we're not talking about going through your hand or anything like that. I know there's transmission matrix people that try to go through super deep stuff, but they can't do 3D. They can't figure out each layer independently. So we're probably talking about stuff that's more on this size scale, where it's a little bit of multiple scattering, but it's not insane. So small organisms is what we've gone after. Organoids is a really big one that people seem to care about in biology. And here's embryos is a good example. Embryos is a great sample for this because they are not scattering. They're definitely single scattering when they're 1 day old. And when they're 3 days old, they're a little bit multiple scattering. When they're 5 days old, they're definitely very multiple scattering. This one's actually my son as a 6-day-old embryo. I have a 3D stack of this too, but they forgot to close the condenser aperture, so it's not coherent enough to reconstruct. And I will forever be angry about that. So human embryos are not that different than mouse embryos. Fruit fly embryos is a really highly scattering one. You can see this just looks like total speckle, right? And they're big. I don't remember which day or stage this was at, but this was a good example of a really tough case. Can we do this? And even confocal can't get through these fruit fly embryos at this particular stage because they're too highly scattering. And so this was like a goal. And Chateau did these experiments. He put a lot of illumination angles in. He had like hundreds of illumination angles for this case. And he can get like a lot of the scattering reduced around the edges, but in the center, it just still looks kind of like mush. So Chateau went after this like application, but then he graduated from his postdoc and went on to start his own lab at UT Austin, where his fix for this was to get a longer wavelength laser. We actually have tunable wavelength lasers. Now we're doing this all at multiple wavelengths, but his lab in UT Austin has gotten some really beautiful images going through a lot of multiple scattering by using all the little fixes that we came out with, figured out as we were going along the way. These also look a little funny, but this is an organoid sample that he's getting the 3D stuff. And you can see there's a lot of multiple scattering here. Don't ask me to quantify it because you can only quantify it on a per case basis, and there's no like scattering mean free path length that's like appropriate to talk about here. And so all of these situations are sort of hand wavy on like how much scattering can you do because it's very nonlinear. It depends on the sample. Okay, how much time is left? I have lots of time left. So computational imaging is awesome, but I have time left, and so let me get into some of the dark secrets. And the dark secrets in computational imaging are that it's finicky. Like, just assume like the simplest case, I have some measurement of something that I'm trying to solve for, and I pass it through some system represented by this forward model A. A might be like a matrix that represents the system or some sort of set of operations that models how light passes through the system. But like, I know what A is. Like, I know the physics of how light propagates through the system. I built the system, so I know how it works. But I spend half my life doing calibration because it's never perfect and we're not modeling the imperfections. So like theory people always like, I added noise and it still works, so it's a robust algorithm, right? But in real life, for computational imaging, noise is not often the problem. It's model mismatch. It's like the lens was slightly misaligned, or there's some like bad pixels on the camera, or whatever else is happening that you need to calibrate for. And a lot of people in computational imaging are spending a lot of their time working on these like pre-normalizations, or like adjusting the like hot pixels, or figuring out what you do with saturated pixels, etc. And all of this like black magic that we spend a lot of time on and then bury in supplement page 5 is really important to get a good result. And if you don't like address it from the beginning, then you're making your stuff less useful. And the whole point of these like dirt cheap hardware, fancy computation that you can just get my code, is that people will use it, that it's really reproducible, adoptable. But it's not reproducible when you have like one piece of duct tape that has to be exactly aligned just right. There's a real example of the first LED array microscope. Lei Chan was the only postdoc who could correctly align the duct tape to get things to work properly. And so we got into thinking about like, how can we go more formally at addressing these problems of model mismatch, not just like noise problems. So for the LED array, we did a lot of calibration, and if we didn't do the calibration, we actually got worse resolution than the native objectives sometimes. So it was absolutely essential. It's baked into all of the images I've shown you. And essentially, the most important calibration pieces we found just like, empirically by playing with this thing and figuring out what was wrong. And the two most important calibration things were the aberrations, like the wavefront aberrations in the pupil plane of the microscope, and the LED position. So you like come in with an LED that's supposed to be at 45 degrees, but your sample's floating in water, and the water surface has a refraction event, and the surface is not totally flat, and so it's 45.3 degrees. So you're shifting in Fourier space by the wrong amount. It causes all kinds of problems. And so knowing these LED positions was really important. And you can like basically brute force it. So you can just decide that I want to not only solve for X, which is my final result, but I also want to solve for theta, where theta is a bunch of calibration parameters. And so then you're like, you want your data efficiency rate to be like, I collect more data than I measured, maybe just a little bit more, probably 10% more is usually enough. And then you can solve jointly for the image and these calibration parameters. In this case, both of these calibration parameters can be solved for just with a big joint optimization of the original algorithm, and it works well, and they're separable nicely, usually. So here's a case where the aberration. So we always compute everything on a patch-by-patch basis because these are humongous images, and it's fully parallelizable. You just take like a 200 by 200 pixel patch, and then take that patch out of all of your images and do this compute to get back your recovered phase at the higher resolution. And we also solve for aberrations here. Of course, since it's patch by patch, we can get the aberrations for each different patch independently, and then we can make a map of the space-varying aberrations in the imaging system. They're exactly what you expect. There's a sweet spot in the middle, and then it gets worse around the edges. Yeah, and so for the 3D stuff, this was absolutely essential. So in 3D, think about like if you have your angle slightly off, if you have like your angle is slightly off, then the further you travel, the more like the more wrong your shift will be, right? And so in 3D, you absolutely need to do these angle corrections. But the really interesting correction that I want to get into, which is our more recent work, is that live samples move, and one of the most limiting factors for this types of techniques is that you need to take a lot of images. So we get this huge space bandwidth product, but we got it by trading time, right? We took a whole bunch of images in order to get high resolution across a big field of view. And so if your sample is alive, then your sample is moving while you're capturing all those images, and you're going to just get like a bunch of garbage, right? So, so here's an example for phase imaging. This is our original Fourier ptychography setup. Took 7 seconds to collect the data. And like there's a lot of stuff blurred out. These are not exactly the same scene, obviously, because this sample was moving and alive. If you collect it faster, you can see more small features. If you collect it with DPC, you get the best resolution on these little features because they're moving around. And typically the smallest stuff is moving the fastest. Okay, so if you think about like what you can do, like a highly leveraged Fourier ptychography, meaning like a very low NA microscope trying to get at resolution that's like 1 NA, takes hundreds of measurements. And so then you can only really think about looking at really slow cell activities. If you have a swimming E. coli, like nothing can do it. You need single shot, basically. And if you have other stuff that's fast, you can have like different amounts of like number of images you can collect before this thing is appreciably moving. These are just kind of my rough guesses. But what M.Eng came out with was, we're not just going to like try to make the hardware faster. We did that as much as we could, and we couldn't get any further. But if we could model the motion, we could correct it. So if we knew the motion, we could sort of like undo the motion and then do our algorithm to reconstruct stuff, and then we could get rid of it. If we knew the object, we could find the motion because we would just correlate each time point image and find the motion, right? So this is just a joint optimization problem. It's a hard one because the motion is not just like rigid body linear motion, it's like warping arbitrary motion. So I'm gonna just show to start the DPC example. So DPC, we started out with 4 half-circle illuminations. As I'm collecting each one, they each have a different contrast mode, so I can't just like register them to each other to find the motion. That's not going to work because they have different illuminations. The registration won't work because different things are bright and dark in these different images, right? But there's definitely motion happening here, so if I just naively reconstruct it, it's garbage, it's all blurred because of the motion. Okay, so we're gonna try to do this like joint optimization. But now, if you just try joint optimization, you need a model for the motion, basically. And it's really hard to come up with a model for arbitrary warping motion. So we need some sort of black magic, which is machine learning. It's not magic, it's science. And this is absolutely a project I would have canceled at the beginning if M.Eng had come to me with it and I was paying attention. But I was on maternity leave with this guy when he came up with the idea, and it already worked basically by the time he showed it to me. Otherwise, I would have said it's not going to work. So what he did was he used these MLPs, multi-layer perceptrons. They're very simple, basic neural networks that he's modeling the motion in the scene with it. And he put all of that into our optimization loop to solve this inverse problem. But these two neural networks are the heart of it, basically, the motion model. So it's like saying now we're trying to solve for x, but now x is a function of t. So if you think about like a worm swimming along, each frame of the video is very similar to the previous one, but everything is moved, like you don't know what direction it's moved, and it's moved by a couple pixels. Each feature is moved by a couple pixels in whatever direction. So we're going to model this now as like the scene is like the super resolved or phase image that you're trying to reconstruct at a particular time frame, so some reference time, t. And then I'm going to solve for a bunch of motion maps that just represent like hopefully sparse array of arrows that tell you how the object moved from time point 1 to time point 2. So I don't need to solve for a whole video. I just need to solve for one image and a bunch of sparse motion maps. And the motion maps must be sparse, so this won't work. Okay, so here's our like 4-image DPC. Our traditional DPC just gives you some blurred garbage, but then now we can solve for we call it space-time DPC. So we solve for the motion, we solve for the object at a particular time point, and then these arrows represent how it's moving over the time that we captured those 4 images. And this is like a nice, we take a few of these in a row. I hope this is, yeah, so traditional DPC will just be motion blurred. You can't see much of the features in here. Phase is hard to see because it's got this like big low frequency phase on top of it. But we can solve for, the image at a particular time frame, and we solve for the motion. So we can interpolate those motion maps to make a video. This is like the video of how this worm moved during those 4 frames. We can actually like interpolate the time like sub-frame, so faster than the frame rate. It might not be right if this thing wasn't moving smoothly, but it is moving smoothly, so it's probably right. Here's another example where we're physically moving the object around. And then I think I can quickly go through the fluorescent version of this, because there's always some biology nerd who wants to know, like, I want to do this for fluorescent. I don't like bright field images. I use fluorescent tags for functionality. I think of phase as structure and fluorescence as function. And the like mathematical counterpart to Fourier ptychography is structured illumination microscopy. So think of illuminating with sinusoids as essentially illuminating with like 2 plane waves coming in from different angles. So it just has a reference beam. That's the main difference there, right? And like we always think about this in Fourier space and how to put things together in Fourier space, but it does have a lot of analogy to Fourier ptychography. So that's kind of the fluorescent analog to Fourier ptychography. And you need structured illumination because fluorophores don't care what angle you illuminate them with, but they do care what intensity you illuminate them with. So speckle sim is just the speckle version of structured illumination microscopy, where you illuminate with a bunch of speckle patterns. Speckle pattern contains all the different sinusoids with different phase shifts. And so you illuminate with a bunch of different speckle patterns, and you can solve the super resolution problem in the similar way in Fourier space. So we're going to do it with speckle because we like speckle, because we do stuff with Scotch tape. Scotch tape has a 0.65 NA in this case. And so we end up this one only had 0.3 NA. Double-sided Scotch tape is different than regular Scotch tape. And several layers will get you to higher NAs. So we're going to have illumination of 0.3 achieved simply by putting a laser through Scotch tape. And then our objective has a 0.1 NA illumination. So it's not super highly leveraged super resolution, but you can get to 4x resolution gain in each dimension, and you get phase and amplitude together. Okay, so that's the last piece that I wanted to get to. This was M.Eng's original idea, was that he wanted to do speckle structured illumination, but he doesn't want to have to change the speckle and you have to take a whole bunch of images with different illumination patterns, right? But it's really complicated to design hardware that can change the illumination pattern dynamically quickly while you're capturing all those images. So his idea was keep the illumination pattern static. It's a speckle pattern through Scotch tape, but let the sample move. So if the sample is moving, then all of these images that you get, then different parts of the sample will see different illumination because they're moving. And so you end up with this big computational inverse problem. Like, can you solve it? We're trying to solve for more than we measured again. So it's you better make sure the information is there. and make sure the information is there amounts to the motion should be smooth, very smooth. And it will sometimes fail. So it's the same idea, exact same motion and scene multi-layer perceptrons. That's our motion model. This is basically just a forward model for motion. You can dump this into almost any imaging problem and use it as a motion model to try to solve for motion. So we got Gokul's commercial structured illumination microscope. If it's wide field, it's not resolving these beads. If I do structured illumination, I can resolve these beads. And then if I shake the table, so we needed the sample to move. Sample was not a moving sample, so we shook the table while we collected the data. And then we get motion blurring in the result. But with the shaking data set, we used our neural spacetime model on it, and now we can resolve these beads again. Okay, so now we can actually look at biological samples. I'm not a biologist. These are samples from other people at Berkeley who wanted to look at particular things. And we can now get them these structured illumination maps that remove motion blur and give them a video of what motion was happening while they were capturing all the data that they needed to get the structured illumination image. So the arrows are the motion maps. It's a 3D commercial sim, so actually, whoops, we can do all of this in 3D. It should be moving. Here we go. So you take about 15 images per depth plane. Oh, it's not playing. Sorry. You take about 15 images per depth plane, so you get a lot of motion during it. Well, I'm going to give up on playing that. I'm basically at the end. My last piece on this particular project with the motion maps is like, it's a little surprising that you can do this. You're solving for a lot more stuff than you measured. It's surprising that this works. It doesn't always work. We should be able to better incorporate priors, like if you know something about how the sample is sparse in some basis set, but it's not super clear how, because these networks are very simple and not easy to change their architecture. But they're also very flexible. They're able to model a lot of stuff that I didn't think that they could. And then the fine print, it doesn't always work. I have tons of cases of total garbage that it spits out. But I think it's a fun direction to explore, and we're trying to make it more robust by exploring different neural network architectures that can do the same thing. So my summary is computational imaging is awesome, but has a lot of problems that we can correct with computational imaging. And so I'm very happy to thank all my group members, collaborators, my anti-collaborators who are here in Erlangen with me, and make a pitch for Micromanager, Picromanager. So Henry from my group used to work on Micromanager software. How many people use it here? This is probably a good audience. Yeah, more people than usually say so. If you use Micromanager, try Picromanager. It's just Micromanager in Python, which means you can easily interface with all of the fancy new machine learning stuff that's out there. So happy to take any questions.
Thanks very much, Laura. Questions?
When you use the Scotch tape, I guess once a while
Well, you should use the microphone.
Sure.
Yeah.
Oh, yeah.
when you use the Scotch tape, I guess once a while the dust will land in there. How often you need to calibrate then?
The dust? Dust
Yeah.
is, I don't know. That's above my pay level. I don't know if they have to take the data really quickly or not. I think they put the Scotch tape between microscope cover slips, so it probably keeps the dust out or lets you blow it off.
First of all, thanks again. This is always so inspiring. Each time I've seen this at some a new layer that just blows my mind. So glad that you're going to be around for some time, because I do want to talk to you about guided acquisition, but I think that's a more technical thing. One thing that you pointed out is robustness. That's a real challenge, right? I know that the computational imaging community is thinking a lot about how we can do the optimization via neural nets now. So have you considered something like domain randomization to make robustness better? So for robotics, that's kind of the way to go, right? Can we do something similar for computational imaging?
Yeah, maybe. I'm not the machine learning person myself. A lot of my students are playing around with these ideas. They're kind of moved past like Fourier ptychography. People did it with neural networks. In general, like you can always, like I have a slide in another talk of like the spectrum between like physics-based versus machine learning-based ways of solving things. And I think that we probably don't want to do either. We want like the best of both worlds. And so like physics-based ways tend to be more robust, but slow. Machine learning tends to be fast, but you have to train it very often, which is pain, and then it makes it really dependent on bias. There's all of these new architectures that I know nothing about and don't know what's useful or not, but my students have lots of ideas. Certainly for the motion stuff, we're playing around with different architectures right now, trying to think about like how to model things like, okay, so these like MLPs are really flexible and good at smooth motion. Because we're making these like motion maps. So smooth motion makes sense, right? So the motion maps are sparse and the arrows are short on each of those. But think about like, I didn't have time to talk about it, but we have a whole project doing this for electron microscopy where we're trying to, so you're doing tomography, this is electron tomography, and you're trying to image individual atoms in this. It's a carbon nanotube and they're rotating it to do tomography. But while they're rotating it, it's growing carbon contamination. Because it's charged, right? So the carbon gets attracted to it. So this is like a rotation data set for tomography. And it's growing this like carbon grass all over the top. And so we've tried these same models on it. In simulation, it works great. In experiment, we have all kinds of problems. But it's not the right model, right? Because it's not a smooth motion. It's like stuff is appearing. And it shouldn't work. And it kind of works, but I heavily suspect that there's better architecture. So they're playing around with different architectures that can model something like this, where the motion is not smooth, but like stuff appearing and disappearing. Or like that's also true for like Palm and Storm, et cetera, right? So one of my students has done this stuff for Sophie, and it worked. He had to completely change the architecture of the model because it's like blinking rather than like sort of like slow, smooth motions. But no, I'm not the expert on which architectures to use. I just let them try whatever they want.
I'm totally convinced that that's like where AI can really help here to make it more robust.
Yeah, I think, robustness is, important. I have some I have some concerns that AI is not robust in a lot of cases. Like if you train on a particular type of sample, then it won't work for another type.
You can have all the kind of the diversity in the training so that you can incorporate that so that the model knows that alignment is always going to suck in many different ways.
Yeah.
You know kind of what.
Yeah, I think that we are never going to have the kinds of large training data sets that like computer vision has to get. Like we might not get to the robustness that those kinds of models can offer because we don't have a sufficient training data. Also, microscopes, like if somebody sneezes and the microscope jiggles, it's a new system, and maybe you need to retrain on that new system. I've seen this a lot. These kinds of like training something, and then like you can't just reuse that trained network sometimes because somebody changed the objective and changed it back, or.
Well, I think a big point of microscopy is to look at something that you've never seen before.
Right.
So in that way, there's a limit to how much. There's a kind of microscopy that you do routine. You want to see what happened to the system. Then you can do these. But real microscopy is for things that you've never seen before.
Yeah, it's a little scary to me to use these like networks that we don't know exactly what they're doing. So like this motion stuff.
But Jona doesn't seem to
example.
be convinced. Doesn't have to be convinced. We have another question here.
I also think we shouldn't ignore all of these things, right? Because they're so powerful, and so we can't just ignore them. That we should maybe like tread gently.
Well, thank you for the talk. And I have a more simple question. Did you manage to combine fluorescent and these images, or your techniques, since fluorescent adds a lot of more contrast to your images?
Yeah, so did I show it or not?
Combine both, or can you take data simultaneously in this case, or do you wait for the fluorescent dye to,
This is simultaneously doing both. It was done like, whoops. actually simultaneously. So we put 2 cameras, one fluorescent camera with a filter and one as the like coherent camera to collect phase.
Thank you for the talk. I have the following question. When you do the layer resolved imaging, in principle, if you, like in the end of the day, you get scattering matrix for each layer, right? If you multiply all the matrices, then there should be like a single layer analog that has the same scattering characteristic of a multiple layer. How can you resolve
This is like the transmission matrix idea, that coherent field in whatever system, like complex field in, complex field out, and there's a transfer function for it. Yes. So that's like what like transmission matrix people do, right? Is they try to solve for the input-output relation. So it's not a convolution. It's not a shift invariant system. It's shift varying system. So I think of like transmission matrix as like looking at the like every angle's output. And from that, you can figure out input-output relationships and make it, yes, you can make it for a given one depth to another depth, you can make it a transfer function.
Yeah, but how can you reconstruct multiple layers if there is always a solution with a single layer?
No, because that solution with a single layer will only work for like one angle, right?
Should be possible to approximate to solve for every transfer.
Then the way you're saying it then is you cannot approximate with a single layer. Because if you come in with some complex field here, you can predict the output with a transfer function for all of that given angle, for any complex field in at that given angle. But when you go to a different angle, it's a different system. You're projecting through a different part of the object in a different direction. It passes through different stuff. And so it's a different system.
Maybe we discuss later.
Well, we have refreshments outside.
If the system is shift invariant, then that is true. So then you can talk about knowing the input-output relationships for any angle from a single one.
So maybe ask a last question and then we can go outside and have discussions. How does the performance compare with existing commercial systems?
Like hollow, like which ones?
I don't know. There's the system from Korea.
So interestingly, the system from Korea is essentially, it started out as like, it's very similar. They just do the outside range of angles. And they started out with a reference beam, and they seem to be like slowly moving towards this like intensity only version. And they also have like their 3D stuff was like, somebody was mentioning to me the other day that it looks like it's like the 3D DPC that does their new 3D stuff. And so like, I haven't dug into this, but they have a patent that's very similar to like the 3D DPC. And that then like somebody was telling me like, that's what it looks like they're doing in their setup. So probably they have better like manufacturing process and hardware. And there's things like only do one thing. They're not doing multiple scattering as yet, I think, but they've been talking about it recently, and I expect that's gonna be in the next version. So, or maybe already is.
So I'm actually not aware of all the commercial systems. Is there another one that?
Well, there's been a lot. Like there was one from EPFL. I don't know if that still exists anymore. And there's a lot of like phase imaging companies that will then let you do tomography. So yeah, I think that like they're getting to a lot of similar stuff. If you have a reference beam, you have a whole different, it's a little bit different, right? So I think if you have a reference beam, you're doing proper interferometry, you're going to have more sensitivity, but you're also more sensitive to environmental junk. And so that's going to depend a lot on implementation. Like how well is it isolated? If it's really well isolated, I think you can do better with interferometry. Yeah, it also depends on the sample size and thickness, right? So we're talking like these LEDs we're approximating them as spatially coherent. And so you get like, there's actually a coherence length. So you want your coherence length to be bigger than your object, so that you're like coherent across the object. So if your object's too big, you'll get a bunch of junk and garbage. But having it be just a little bit bigger than the object is actually an advantage because you get rid of all the speckle from the garbage that's like inside the microscope at other planes versus a fully, totally coherent system. So like how the implementation, like even just like what size of LED you choose makes a humongous difference. And so like we've never done direct comparisons because we're interested in the ideas and the concepts, not so much in like making a product. But actually what I've seen from a lot of the companies, they're kind of like converged to similar ideas in the end.
There's only one Maxwell's equation. All right, well, thank you very much.